Our next topic is actually is taking a little bit different topic in terms of climate change and the effects that we might expect on our landscape here. Our next presenter is Klos. Klos is a PhD candidate at the University of Moscow in Idaho. He is studying hydrology and climate science and looking at interactions between humans and nature within that context. I came in contact with Zion and his crew of traveling vagabonds. In Missoula, about a year and a half ago, they were traveling and doing some workshops in communities to do some public education and outreach about local effects of climate change in people's specific communities. And so I really appreciated it in that context because we hear a lot about climate change effects globally, regionally, generally on the landscape, but to actually be able to visualize it within your community, I think really hits home. So maybe Zion can share a little bit similar to what he shared with us back then a year and a half ago. And I guess I would also say sometimes presentations on climate change impacts can be really sobering. And hopefully it also moves us to action as well this morning. So, Zion?
So, like I mentioned, our group of traveling vagabonds, myself and other PhD students at the University of Idaho, all working together with a group of dedicated faculty as well at the university and across the state to basically travel around Idaho and Montana. We did a series of workshops. These took a whole day. We go into a community, work with community members, federal agency folks, state agency folks, county level, city level, talk about global climate change and really what it means at more of these local and regional levels. So looking at changes in temperature and water, vegetation, wildfire, a big part of our landscape here in Montana and Idaho, Northwest, and then getting down to a much more local scale and what we can maybe expect, these finer scales and what our natural resources may look like going into the future. And really what we're trying to do is partially help bring the best state of the science to the people of these areas so they can make decisions on their own about what the future might look like and give them as a chance to talk in groups and think about, okay, well, what are some ways that we can maybe adapt to these changing systems? So I'm excited today to talk to this group, which is a little bit on the other side of it. How do we think about changing what it is that we put into the atmosphere that's driving this whole system? So today, I'd like to talk a little bit, instead of doing a whole day workshop, I'm going to kind of try to condense down some key parts into 20 minutes or so here. And I think it's good to reiterate, it's quite the day to be talking about global warming when it's minus 15 outside. But I think it's also a good time to remember that the reason we call it climate change and not global warming anymore is not necessarily trying to get out of that bad word, but because it's a lot more than just the change in the average going up. It's also a change in variability. So a good paired part of climate change is it's partially global warming and partially global weirding, might be a way to call it. So that's what I like to say. So the variability is also going up at the same time that the average is moving up. So we're seeing more extremes on both the hot and the colder end, seeing snow going to places never really had snow before, especially in the southern U.S. So here's a little background at a global level, and then I'm going to zoom right into kind of more our region. So climate change, not new to Earth, but new to us. My background's in geology before I was at the University of Idaho. So I like to think about it in the scale of millions of years, but particularly looking at the last 1,000 years and the last 10,000 years on that kind of right side of the graph. It's a logarithmic scale there. And so you look at the last 10,000 years, and we zoom in just to the last 150 years here. And I think a lot of you have seen this graph before. You really see some drastic changes, especially from 1980 onwards, where we see this rapid upward trend in global average temperatures. Now, the globe's been a lot warmer in the past, as you can see, going back millions of years, and it's been a lot colder in the past too, with previous ice ages. But what's new is in this last 10,000 years, when us as humans have existed on the planet as a civilization, we haven't seen temperatures to the place that we're at now and where we're going. So that's where we're saying it's new to us. Yeah, the planet's seen it before, but have we seen it before? No, it's something that we're starting to adapt to for the first time. So we zoom in now to our region, northwest. We see both. So on the left there, we see that again this kind of trend from 1900 to today. Temperatures are getting hotter across the region, particularly over the last 30 years, just like we're seeing at the global scale. So that's reflected here as well. And then if you take that graph on the left side and you put a trend line through that, if that trend line was going up through time, you're going to have a red dot on that right map. And if that trend line is going down over time, you're going to see a blue dot. So it's cooling. You can see most places in our region are cooling, and the larger the dot, the larger, or sorry, they are warming. The larger the dot, the larger the amount of warming. And so there are some places that are still cooling over that trend line, but for the vast majority, it's warming and warming by quite a bit. So the increased temperature is observed for, again, most areas in the region, but there is local scale variability still. Now, warming temperatures aren't necessarily all a bad thing. I think it's also a thing that we come into climate change talks thinking all doom and gloom. Well, yeah, it's bad because things are changing. We have to adapt to that, but there's also advantages to change as well as disadvantages. So one example, frost-free growing season. The growing season in our region is getting longer over time. Again, the last 100 years, and then the average growing season, and then the change from that average increasing, especially over, again, the last 30 years, getting longer and longer growing seasons. Now, this is great if you have the water at the same time that you have the temperatures. So that's where advances in irrigation and advances in ways that we can get that water to the places where we can grow the crops is really important. So, thinking again about a little more on the agricultural side, big issue, especially where we're at in the Palouse, is erosion in the springtime. We want those fields not to get inundated and then inundate too fast with water and erode. So this is the intensity of precipitation over the last 100 years, and this is the largest event for any given 3 days of the year. So if you take the most rainfall that happened at any 3-day point in the year, the largest one for each of these years over the last 100 years, you can see that the intensity of precipitation is getting larger and larger. Now, that's the intensity. The overall precipitation is much more variable, and it's hard to pull a trend out of through time, but this intensity we're really seeing going up. Now, we change from the intensity of precip to what type of precipitation we actually have coming down, and what we see is a decrease in the percentage of snow and increase in the percentage of rain. So in this graph, we don't have this data going back as far, but here we have 1960 to 2007. This is one mountain range in southern Idaho. You can see for, say, given year 1965, that first year, about 35% of precip came down as snow, and 65 came down as rain. And then you go through time, and that percentage of snow goes down on average, and that percentage of rain goes up on average. So winter snows are changing the winter rains is kind of the take-home message there. And here again, a map of our region. Looking at individual snow course sites, we're looking at how much snow is on the ground for any given month of the year. And these dots are just same as one of those first maps I showed you. If they're red, that means that snowpack is decreasing. If they're blue, snowpack is increasing. So on the left is January measurements. So someone went out into the field, measured the depth of snow. This is the NRCS doing this. They do it every month, and they've done it for the last 100 years or so in a lot of locations. You can see a lot of spots in January you have a variability. So some places are getting more January snow, and some places are getting a little bit less January snow. Now you look at the right side on the April measurements. So every April for the last 100 years, we're seeing some much more drastic decreases in the amount of snow left by April. So there's a large decrease in snowpack on April 1st, and this doesn't really mean that the rate of snowfall is decreasing overall. In the winter time, as you can see there on the left, there are a lot of places where that snowpack is going up as well as going down. But it does mean that the snow is melting sooner, and a lot of those late season snows are changing into rainstorms instead. Now we think about, so we move from temperature, precip, now into snowpack, and now finally what does that mean for actual stream flow and the water available in stream if we're thinking about irrigated systems. So a big change is we're seeing changes in the timing of that stream flow. So here's spring peak flow. So what day of the year do you have the largest amount of flow in your given watershed? And we're seeing across the region, on average, those are going down over time. Getting earlier in the year, and that's again because a lot of that snow is shifting to rain, and it comes down instead of staying up on the mountain slope. It melts off, comes down into the rivers earlier, and not just the timing, but also the total amount. We're also seeing decreases over time. So there's decrease over the last 50 years in average annual discharge. However, the amount of variability in discharge between years remains high. And this is a key point I want to bring out here is, so this graph is showing a downward trend, but if you look at the high points, there still are some of the same large flows that we've seen in the past. I mean, they're just not maybe happening as often, but those dry flow years at the bottom of that graph, those lower values, those are becoming more common. So we're seeing some more of these really intense drought years in terms of in-stream water becoming more common, and not as many of our really wet flow years, and the average is going down over time. And so that's the past. Just kind of throw it out there. I know it's a little doom and gloomy, but it's a good information to know because it helps us think about what we want to plan for it going into the future. And that's really why we're here, trying to help people understand what the future might look like. And so that's where I'm going to shift now and talk about what we have seen to what we think we're going to see going into the future. And this involves a whole different type of science, because instead of looking at historic data, we think about how do we model what the future looks like. So we're going to look at projected changes from present to future here quickly. So it'd be that right side of that graph where you see a lot more variability. And so I'm just going to break down a little bit, just a little background really quick about how do we figure out what the future holds. How can we tell what it is, and really what the future holds depends, and there's a lot of different options, but I want to help us think through ways that we can think about it more concretely. So on the bottom of this graph here, we have a future climate projection. How do we get that? Well, there's actually two main parts. There's this global emission scenario, or like a storyline about how much greenhouse gases are going to be in our atmosphere into the future. And then there's the global climate models, which you probably heard about, which take the amount of greenhouse gas from that storyline and then say, okay, how much warming is that actually going to create, and where is that going to happen? How's that going to change precip, everything else? Now, the uncertainty with these is a key part I want to highlight, because we're actually getting pretty good at these global climate models. There's about 13 major ones out there that are being used, and they all end up being compared against each other every few years. They're advancing really fast. They're going to be really accurate. But unfortunately, our final future climate projections are still very inaccurate, and that's because we don't have a very good handle on predicting the future of global society in terms of how much greenhouse gas are we going to have into the future. And as you guys are all at this conference doing, we're trying to figure out, okay, how do we change the type of energy that we use, and that's a very complex system that's very hard to figure out. So as good as we can get at the science side of it, it's still going to be really hard to get that kind of social science piece where we figure out what the future looks like. So this is how we think through it in the climate science world. Here we have a graph showing the amount of heating, or essentially how much greenhouse gases will be in the atmosphere from 1900 to today, and then how much going into the future. And there's some options there. Those options are called emission scenarios. They're only an estimate of society's additional atmospheric greenhouse gases into the future. And often you'll see these three. So if you're doing anything related to climate change projections into the future, you're reading any type of white paper or just out there on the internet, you'll often see A2, A1B, B1. A little bit of jargon, but I wanted to put it out there just so you know what it is when you come across it, if you do. So what these emission scenarios are essentially is B1 is more of your utopian society into the future, more of a moderate, and then more of an extreme in terms of how much greenhouse gas we're putting into the future. So A2 scenario, kind of business as usual. A1B, we're getting a little bit better. We're balancing some things out, more alternative energies coming into the system, alternative fuels, and B1 being like, we did a really great job. Like starting today, we are going 100% renewables. So we have also these little RCP, which is as of the new IPCC report. If anyone gets too technical with this, I just wanted to throw that out there. They actually switched. They don't use these scenario names anymore. They use RCP 8.5, 6 and 4.5, which means how many watts per meter squared of heating will you see by the end of the century from increased radiative forcing. But that's a bunch of technical stuff. Don't need to worry about that. All you need to worry about is what I'm going to be showing you, which is what we see happening by mid-century for our region. And it doesn't really matter which scenario you use, because by mid-century, by 2050, there's not that much difference between the scenarios. It's really by the end of the century. So what we do today in terms of reducing greenhouse gases are going to have a big effect on the end of the century, but we're pretty well locked into what's going to happen by mid-century. That's because especially the oceans take a long time to heat up, and there's a lot of big circulation patterns that make this large buffering effect that takes a while for the whole system to really get into full gear. And then a little downside, so these were created in 2000, and we're actually currently exceeding the A2 emission scenario in 2012. 13, we're getting up a little higher, and we're getting a little bit better next year coming into it, 2014. We'll see what happens going in, but we're still up there pretty high on the extreme end.
So the units are on the graph.
Oh, sorry.
That last one.
The units on the graph are just degrees of Celsius heating. I took the units off just for simplicity, but it's just basically saying at a global average, how much heating would you see associated with this change in emissions?
Is each line on the left 1 degree Celsius?
Yeah. Yeah, sorry about that. But yeah, the main part is we're seeing it going up across all of them. So, what does it look like now for our region going into the future? So, here we have this graph. I'm going to actually step through it in detail for everyone. This is the one that the units are important. So, change from current to mid-century, temperature change, and this is degrees Fahrenheit for just the Northern Rockies. So, if you take just the Northern Rockies, so here we're talking about western Montana, Idaho, kind of greater Yellowstone area. So we have one emission scenario, so this is B1, a little bit more the kind of utopian one, and then we have one dot there that represents the average temperature change from now to mid-century, so the next 50 years or so, for the Northern Rockies. And so we say it's going about 5 degrees Fahrenheit on average, and that's for just the winter months of December, January, February. Now we build this out a little bit, put a little box plot in there, and now this is showing all the global climate models, the major 13 of them, put into a box plot. You can see on average, we're going up about 3 degrees Fahrenheit under this one emission scenario for winter. So this is where we're breaking up, because there's emission scenarios, there's global climate models, and then there's averages of all those. So that's why we move into this last part. Now we look at just the winter, and we look at all 3 of these scenarios. We have, again, the B1, A1B, and the A2, and they're all showing between about maybe on average 2 to 3 degrees Fahrenheit of warming for the winter months over the next 50 years. And now we zoom this graph out and look at all the other months. So it's a lot if we threw that at you all at once, but hopefully you can see kind of what this is showing now is there's multiple global climate models. Often we just use the mean of those to look at that middle of those box plots. And I think thinking about maybe the A1B or the A2 scenario might be the better place to look about where we're going. So we're seeing projected changes in temperature are highest during the summer months, although all seasons are expected to get hotter under every model and every scenario. And that's the kind of take home is there's a lot of variability in the predictions, but they're all showing it getting hotter. Now you take this same graph and we think about precipitation instead of temperature. And so this is changes again by mid-century. So we have winter, spring, summer, and autumn, those same 3 different emission scenarios and the same set of GCMs. But instead of the 0 being at the bottom of the graph like the previous one, now our 0 is in the middle. And so we can see for winter and spring and autumn, we're having increases in precipitation, slightly, maybe around 5% or so. And then for summer, we're seeing decreases somewhere around maybe 10%. And so summer precipitation is expected to decrease, while precipitation, again, those other regions start to slightly increase. Now the question is, will the precip increases be at a rate fast enough to offset the increased warming in terms of how much water actually gets taken out of the landscape, especially in mountain environments? with a lot of trees transpiring all that water out. This is some work that I'm finishing up now for my PhD, looking at not just the temperature, but what that temperature means for, are we going to have snow on our landscape, or are we going to have rain or some kind of rain-snow mix? This graph shows historical on the left column by mid-century on the right, and if it's blue, that means it's a rain-dominated area there in the northwest, and if it's red, it's a rain-snow mix, and if it's white, it's snow-dominated. You can see pretty much, especially for western Montana, we're looking at that November through March really being a snow-dominated landscape historically. Now we take that to mid-century, we're seeing that change from 5 months more to about 3 months of the year, from December through February being snow-dominated, where November and March are now kind of in that rain-snow mix. Now we're going to zoom that in to our own landscape. So here we're zooming in to the Bitterroot Valley, looking at Missoula from the south. That's the National Forest boundary. In red, that's the area that's a rain-snow mix historically, and all the clear area is snow-dominated. That's in the past. Now we move that rain-snow mix zone into the future, and this is for the mid-winter months, and you can see moving kind of up the slopes, a lot of that previously snow-dominated area is now shifting to a rain-snow mix. And so a lot of the landscape that previously had a snowpack all of wintertime now may see more of a snowpack come in, but then maybe get washed out by rain, so on and so forth, and a lot more variability in those areas. But those high elevation areas are still staying the same. Now I'm going to stop this. We show all the other sites that we went to and show the same thing. But I made some maps here for around where we're at in western Montana. So there in the center is Helena, dead center in that map. You can see there's some red on the left. That lower left red is, again, the Bitterroot Valley where we were just looking. And then the bottom right is near Livingston, and to the east, you can see those are really the only areas historically where we've seen a rain-snow mix. The rest of the region is snow-dominated for the winter months. Now we take the historic climate and look where we're going to be by maybe mid-century. And this is under the modern scenario. You can see a lot of the valleys basically are moving in from previously being snow-dominated to more of a rain-snow mix. Now a lot of the higher mountain areas are still staying snow-dominated, so you might still see a lot of the same snowpacks. You take this out to the end of the century, you might see a lot of that mountain area move in as well. But a lot of your lower elevation mountains and a lot of your valleys are really seeing these shifts from more of a snow environment to more of a rain-snow mix for the winter time. Zoom this out to the whole Northwest. Again, historically, Montana, Idaho, a lot of snow-dominated area. We move into the future, we now again have this rain-snow mix moving into a lot of the region. And some areas is going to have a bigger impact where you're really dominated by your winter snow providing that water resource. But there are other areas where you get a lot of summertime rains. Not going to see as much of a change in terms of total water resources, but a lot of changes in the timing of those resources. And then I'll finish off with one more here. We're moving again from snowpack to what that means for stream flow. Here's projections into the future. This is a great resource from the University of Washington. There's local scale projections for the whole Northwest. You can probably find a watershed near you on this website. Have it up again at the end to show what the future might look like under some different scenarios for your area. So in the red line on this graph, we're showing months of the water year from October through September and the amount of stream flow for any given month. You can see it peaks kind of in March, April, May historically, where that snow is melting off. Maybe more into June, the highest peak, and then you look in that's the blue line, and then the red line is by mid-century, we're seeing that peak get earlier and become less. So we're seeing a lot of that snow again shift to rain, come out of the watershed sooner. And then what does this mean for flood risk? So historically, again, is in blue, and this is showing the size of peak flows for a given reoccurrence interval. And so this is how we talk about floods in kind of the hydrology world, is how often do we see a flood of this magnitude of CFS. So a 4,000 CFS flood we maybe see every 20 years on this watershed. That same kind of flood that we saw every, say, 50 years is now something that we're going to see more maybe every 20 years or every 10 years, we're seeing the size of those floods really increase. And there's multiple projections because there's multiple models and scenarios, but again, all those are increasing. And that's I put in one more for kind of the crowd here, also looking at projections in soil moisture. By kind of mid-century, seeing a decrease. That scale is, the darkest brown is about 30% decrease in soil moisture, but again, that's for more of the mountain areas, which will have effect in eventual downstream water, but a lot of those valley areas where the irrigation is going on, and a lot of agriculture, the dryland agriculture is going on, we're not seeing the same level of drying. That's a lot because we still have a lot of those big convective storms in the summer providing some water in the system. So, final takeaway from all of this, can we work with this level of uncertainty? Here's an example. So, we put out a lot of information, a lot of facts, but the main takeaway I want you guys to have is you go to your doctor and say, well, the doctor says to you at the clinic, well, I'm very concerned about your heart condition. I think you should be on a lower cholesterol diet and exercise. Now, would anybody say to their doctor, you can't tell me precisely when I'm going to have the heart attack and how severe it will be, why should I change my lifestyle? Answer is no. Yeah, we can work with this level of uncertainty. This level of uncertainty isn't going to go away in a few years with better science, because we don't know what future society holds in terms of greenhouse gases, which is the main place the uncertainty is coming from. But we do know that these changes are happening in this relative way, and so we can think about those relative changes and the changes in these systems. That's where we can start to think about adaptation and be prepared for the uncertainty that's out there. So, with that, I'll leave you with some resources in case you want them for some of these more regional scale stuff. I have a website as well. You can email me. A lot of this information is up there. So, again, thank you very much.